Alright, so here we are. I'm going to wrap up this long stream in the next hour or less, maybe a half hour. What time is it? Probably in the next half hour to hour. And this will be the last video from this stream that I post. Now, what I just finished doing was deciding that the skip unchanged deltas optimization not good enough to keep. So, there we go. Undo the skip unchanged deltas code. There we go. Now what? Now we need to think of a new thing to try. We could try building the propagation, like building the coexistence tables, so that we don't have to do any work checking if two cells coexist properly, can coexist or not. We can just look it up in the table. Still not totally convinced of the effectiveness of that method. One thing that might be better is to do the pre-propagated thing for finished cells, which is the idea that we could pre-compute how all the neighbors should update immediately if we know that a cell just finished, right? Which is not too hard for us to figure out. You know what? Let's do first. Let's remove the finished table, because as I've pointed out many times, we have sort of redundancy there, because now we can do that by just checking if the cell base is equal to 1. So this is the same as saying why the hell is it okay, there we go. Cell finished. So cell base. Feasible states. Yes. Feasible states times cell stride equals 1. Perfect. So let me make sure that that still operates the same way. Not so perfect, actually. What's that all about? Do this again, but do it more carefully this time. Oh, I already see what the problem was. Perfect. Awesome. So good. So cool. All right. Whoops. Not what I wanted to do. Curious if the time is any better. Certainly the code is simpler anyway, so I'm going to keep it this way. Contradictive state on the board, huh? You're talking about right up here with these X's. You're saying you couldn't find a way to make this work. Oh yeah, because you don't like putting things flush against the edge of the room, but you're set yourself up to where you're going to have to. Either that or you had to... Yeah, you didn't really have any options here, did you? Screwed the pooch with this move. But, ignoring that, all the rest of these generator runtimes are interesting. Because they all appear to be slower. Why would they all be so much slower? Is it because it's harder to index into that big array to check these things? Is it actually slower, or does it just look slower because of random shit? If it's actually slower, we'll keep it. We'll keep the finished array. Okay. Probably dropping a bunch of grids on me, isn't it? Oh, no, there we go. Ah, it's still slower. But what's slowing it down? It was just faster a moment ago, and it wasn't hitting this contradiction. What have I changed? What else did I change? Changed all this mask stuff. I had that. Ah, shit. See, that right there is wild. That's so weird. Because now... What the hell was that? Well, that's weird. Not sure what the deal was there. Anyway, so now that's back down to the right range of speeds. Something in between all the undos and then the things I did had some kind of effect. So keep all that stuff. Now let's go through and say, suppose I have completion stuff, right? Let's take out all the completion stuff again. Let's take out all the there's another one. Completion stuff. The out finished stuff. Take out this. Take out all that. Take out 100% of that. And what you get at the other end runs at the same speed, right? Yeah, roughly speaking. I mean, we got a spike there, which is odd, but all in all, it's still just as good. Winning in a few spots, losing in a few spots, as it was before. Not really anything major. And so that's interesting. So then I went and deleted all of this. Deleted all of that. Deleted all of this. Deleted all of this and this. Okay, just double check. That's still the same speed, right? I mean, I just deleted code that wasn't compiling in anyway. Yeah. Perfect. Okay. So then, if I take the self-finish stuff out again, what happens? Let me replace that if with this one. Okay, so that's running at the same speed, right? Yeah. Yeah. So some kind of quirk or something. Things were running slower for a moment. Don't know. Let's go ahead and make that permanent. Okay, just deleted code that wasn't compiling, so that shouldn't change anything, right? Just double checking. Good. Okay, so now, um, okay, um, ooh, I think I just came up with a nice idea. Interesting. This kind of requires some heavy-duty creativeness to pull off. Actually, it can't be possible. Yeah, a general solution version of what I'm thinking of can't be possible. But we can make a specialized version of it. For sure. Okay, so, okay, so now, we don't use the self-finished array anymore. Would we still, right, the thing I also changed that I haven't changed here yet is, let's rename this to cellbase. Rename this to cell, and get rid of this completely. Cellbase. Cellbase. cell base, cell, cell base, cell. Okay, cool. So that's still the same speed. Now what I should start doing, now that I take a moment and think about it, is I should start building with optimizations turned on, so that I can, you know, get the more important results of how fast this is that are actually, you know, legitimate. So scratch, run that again. Here we go. Here's where we really are. Alright, cool. Now, speeding up the propagation is still the most important thing we can do. And I have an idea for how to speed up propagation, but I don't think I have the energy to do it tonight. But I can explain it to you. Now, the general solution to this is actually impossible just because it would go out to infinity in certain cases. If you did it generally, you would say keep going until you run out of information. But there are certain cases you could construct with very carefully constructed sample sets where you would always know what had to come next after that and what had to come next after that. And I guess if you know the output size, you could use the output size as your upper bound. So you could do a sort of like a thing where you say, all right, we're going to do the special version of we're going to do the slow propagation, and then that just figures the whole thing out anyway. But what I was thinking you could do is the idea that the C# version used to speed up the checks for coexistence was that it would say something like, all right, suppose we've got this is the thing we're testing, the area we're testing, and here's the center, right? And it would say, all right, delta x is -2, delta y is -2. Here's the given that delta x, delta y, here's a subtable where you can plug in two samples, and it'll tell you whether those two samples coexist in that orientation or not. Now, the reason I don't like that is because it's not like the actual sample overlapping test actually takes that much time. What actually takes so much time is the fact that there's just so darn many tests to do, right? So, for all I care, the time it takes to look up a 1 or 0 in a table that's like four-dimensional is not that compelling to me. You could maybe think that, oh, that's going to be a little bit faster because you're going to be looking in the same area of the table over and over again, then you're going to move the x over 1 and look in the same area of a nearby table over and over again, and so on. So it's got some cache locality to it, whereas doing just the straight out overlap testing is not as forgiving, but that's actually not so clearly true to me either, because you're actually testing the same sample against a bunch of the other samples over and over again. So that one sample stays loaded in while the others come in, and you load that and test it against it over and over again. And you're just testing one or two or three or four or six at the worst positions. And looking at the timing of it, it was minuscule, the amount of time it was spending actually doing the comparison. So you maybe could save a little bit by doing the lookup table, but I'm looking for a more clever, deeper way to save stuff first. It might be that I'm spinning my wheels on something that someone else has already determined is that there's no other way to do it, but I'd like to do that for myself. So I'm going to keep spinning my wheels for a while. Now, my idea here is, what if you did make the lookup table, but you put more information into that lookup table? Same lookup table, it's four-dimensional, but you do even more stuff. So the way that they, in the C# code, generated the lookup table was just to say, alright, if this cell is right here, and I've got a position here, right, then I can just look up, basically given this dx dy, I can look up, if I know the sample values for this cell, for each of its sample values, I can look up, does this sample exist for this sample or not, right? And basically if you have more than one sample existing in this cell here, then you have, then all you have to do is say, alright, it's the OR of all of those samples, right? If this sample allows it, or this sample, or this sample, or this sample, if none of them allow it, then you can finally say, okay, well, this sample, this pink sample then isn't allowed. There's no way to get this pink sample to be allowed because I've checked all the green samples and none of them allow this particular sample to exist here, right? So it's an OR. And pre-computing the OR of all of those tables isn't going to be fast enough. It's something I considered, because you could imagine if you pre-computed the ORs, then you wouldn't have to loop through all of the green cells' possible sample values, but you still have to do an OR of a very large table that's, you know, greater than or equal to the number of pink samples you're going to have to try anyway. But here's an idea. Maybe instead of thinking of it in terms of let's reduce the complexity in terms of the number of comparisons we do, you can also speed it up by saying let's prevent it from having to do so many changes that bounce back and forth to each other for a long time. And the way you could do that is by communicating more information and knowing that you can get rid of samples more sooner, right? So if I have to change the same cell 3 times to learn all the things I can remove from it, like, that's no good. If I can just do it one change, then that's 1/3 as much work, and I all at once learn that all of these different samples aren't going to work. That would be really good. So how can I do that? Here's an idea. What if I say, instead of figuring out by just saying, suppose I put this sample here, and I put this sample here, and asking, do they work or not, right? Instead, what I do is I say, let's do a little bit more digging than that. Let's suppose that I have a big, empty, open field, right? Nothing has been decided yet. And I set this to be T1, right? I pick whatever sample value I want, and I say, put that sample right there, okay? And then what I'm going to do is I'm going to say, alright, well, let's start fanning out and do the propagation. Do propagation the way I'm doing it now, the slow way, right? And let's see how far I can given just that one thing, how far can I propagate this out, right? And if I do that, what I learn is, well, if I know the particular value for this cell, then I know a set of values that can show up here, and I know a set of values that can show up here. And those two don't really have any relation to each other, since they are both complying to the same, this and this here are both complying to the same thing, right? This is complying to a set of possible values, this is complying to a set of possible values. But it's not quite that simple, because there's also this guy here, and he has to be one of the samples that exists that complies with those those 4 squares there, right? So if I back up for a moment, um, um, oh, whoops, I did that pink square the wrong way. So here's a different, let me do this pink square more precisely. Doopy-doo, doopy-doo, doopy-doo. Right, so they have this 2x2 overlapping section, and they don't really, it doesn't matter to them that there's no sort of communication. If he picks his value as something, she doesn't care what that it turns out to be. She's got all the information she needs right here, and no decision he makes can really affect the information she needs to make a decision based on, right? So her decision won't be affected by his decision, basically. But what's interesting is there is somebody who kind of does affect, actually, where that effect actually does exist, and that's this guy here who overlaps with both of them, right? You put that guy down and you go, well, he only cares about, let me draw that more precisely again so that it doesn't look cluttered. Doopy, 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 doo, doopy, doo. Right, so the idea here is, what does he overlap with? Well, he overlaps with these two, and he overlaps with these two. So whatever decisions are allowed for this pink guy here affect what's allowed for this orange guy here, which affects what's allowed for this pink guy here. So just looking at these two, this 2x2 overlap for this orange guy doesn't give us as much information as we could learn about that orange guy. And furthermore, just looking at that 6x6 for that pink guy doesn't necessarily give us everything we need to know, because maybe this pink guy only has one possible value he can ever take, and that means this orange guy only has 2 possible values he can ever take, and that eliminates some of the pink values that would have been possible here, right? So we can actually build a smarter lookup table, I think. And what I think we'll do is we'll just say, let's not try to go to the end of the world. Let's just say we have a 5x5 region. Let me pick a new color. We have the 5x5 region, or the region that is based on whatever sample size you're using in whatever particular case you've got. But in this case, it'd be this region here, right? And we say, let's look at this, and let's just learn what we can. Supposing that the rest of the samples, they don't wrap, they hang over the edges, and say, put T1 here, and then from that you learn, okay, well, here are the set of things that I think can go, whoops. You pick any cell you want. Doesn't matter which one you start with, but you've only got 25 cells to work on. The center one you pick a value for, you pick a sample for, and then you go, alright, suppose that all the other 24 samples could take on any cell value. Let's just start going. Can he take on all the values we're saying he can take on? Yes or no? And then you eliminate the things it can no longer take on. Then you go, alright, this guy right here. Process him by comparing him to the center guy here, right? And so on. And you keep doing that, processing everybody, comparing them to the center to reduce the number of values they've got. Then what you do is you, one at a time, you say, take this as the center, don't go outside of this blue square, but anything inside this blue square that overlaps with this pink square, update them according to what he believes, and keep on, and then you do the next center, and keep on changing the sort of nearby centers, and try to get the most, until you can't find anywhere else that you can reduce, that you can deduce, oh, this has to happen this way and whatever. And the reason that's useful is, even though once you go and apply it, you're still going to have bouncing back and forth, it's only going to be long range bouncing back and forth. Over the short range, it'll be able to say, given that this cell, if this cell had this value, these surrounding things have to do one of these things. Now you can still OR those together, right? But the OR will be less sloppy, and so it will converge more quickly. That's my plan. That's what I think I want to do. And I think But that is all I have for today. I just don't have the energy to actually implement this, I don't think. I mean, what we could do is just start by doing the simpler version, which is to set up the table that drives this whole thing, and fill it using the sloppy lame method, see if we get any speed from that, and then do this next time I make one of these videos, which will not be live, by the way. So let's do that. Let's make let's drive everything through a table, but let's not do the fancy table. Let's do the original C# table, and I'll leave the fancy table for a future video. State. Alright, what I want here is a uint8t table called Coexistence table. Perfect. And what we'll do is that coexistence table, when we let's see, we initialize the state there. When we initialize the state, we're going to fill the coexistence table. So the coexistence table, well, do we have the memory we need? Wave 2D state memory. Coexistence table, push the array that you get from the states partition of type uint8t, and how many of them do you need? Well, okay, so first of all, let's just do the whole table the big way. So that would be dx range times dy range times sample count times sample count, which is huge. And let's see, dx range is samples sample width times 2 minus 1. dy range, same thing. Perfect. Does that run? Okay. What if I mem set this to 0? Just making sure that this isn't overflowing those memory bounds, because it's kind of a big table. Perfect, it's working. Okay, now, given that coexistence table, let's fill it. So the way we're going to fill it is, we're not going to mem set it, we're going to for int32d delta x equals, so here's where I start to need sample width, sample height, And then let me pop over here to get delta x, delta y. Right, so we do that iteration there. So at each step of the way, I'm going to make a quick pit stop to grab the relevant subtable, which is just go to the coexistence table at delta x plus delta y times, yeah, I need like a state, wait, no, that doesn't work. Delta, yeah, I need like uint32 c coex table x shift equals sample width minus 1, sample height minus 1 is the coex table y shift, and we need coex table line stride, which is going to be same as thing as dx range. Okay, so dx range will work for that actually. Yeah, so we need delta x plus coex table x shift. Let's make those integers. uint32 tx equals that uint32t, place x with y, coex table tx plus ty times dx range, and then all of that times coex table stride, which is just the sample count squared, the distance from the beginning of one table to the beginning of the next, so coex table stride. Right. Alright, so that gives me the beginning of the subtable I care about, and then what I can do is loop here, uint32 t1, no, t2, how does that loop work? Yeah, t2 and then t1, sample count plus plus t2, then t1, and that way you can you take the subtable, t1 plus, technically what I really ought to do is that, t1 plus t2 times dx range, no, t2 times sample count equals result. Now what's the result? The result is the same thing that you get when you do this whole shenanigan here. So you need this for one thing. You need that as soon as you've got a delta x, delta y situation on your hands. So you compute min x, min y, max x, max y, and you use that to iterate over sample 1 and sample 2. Now where do you get sample 1 and sample 2? Get those right here. So the coexist check, you get sample 1, sample 2. You iterate over the overlapping area. You see if they match or not. You're looking to see coexist check result will come out as 1. Coexist check result goes into the subtable. So there you go. The idea is implemented. Right. So now, let me see if that runs. Yep, that runs with no problem. You can see it certainly took a lot longer than usual to do the generator init now, because we're doing all that pre-processing. But now we're going to go ahead and pop over here, where we're going to find that we can stop doing a lot of the work we're doing. So no more of this. Alright. We don't actually need this. We don't actually need this. So all we need is I need a subtable into which I can plug T1 plus T2 times sample count. That's the coex subtable. And where does the coex subtable come from? The coex subtable is cell2 base up here. Before we start any amount of work, we want to grab sample width. We need to fill out all this other stuff. So the dx range is this. The coex table stride is this. The shifts are these. Right, so these are for using coex table, and we can also imagine grabbing the coex table itself as just a local. So that would be something like uint 8t coex table equals state coexistence table. right? How are we doing? Alright, so we come down here. Ah, I do need x2, y2, huh? Okay. I need x2, y2 because of stuff. So here we go. x2, u into 32, y2. See if I can remember how to get these. These are what you get when you cast. And you get them by taking the change, oops, change.x plus delta x, and then in this line you make that delta y, and then you modulo that to the output width or height, right? You're taking oh, and then you need to add that in there. There we go. So that gives me x2, y2. Now, it's going to complain about the coex subtable. It doesn't see such a thing. But that's just because it's being silly. It can find the coex subtable, just like this up here found the subtable. The way you get a subtable is you take your dx, your dy, and you get the subtable, right? So, coex subtable equals the coex table, tx plus ty dx range times coex table stride. Now to get tx and ty, we're going to take those, add those. There we go. Coex subtable. Ah, there we go. Boom. Alright. Okay, that is quite a bit faster. Actually, I have to eat my own words. It's quite a bit faster. I'm confused now because all the timing I did suggested that wouldn't be much faster. I guess if that timing was only half the propagation, that shouldn't be any less than half. That can't be less than half of these, but it is. Well, okay. So let me just do one quick thing. Turn off this. Run that again. Awesome. So yeah, that just generated 10 awesome rooms that appear to follow all the rules still. Yeah, it's still making that room at the beginning, which is awesome. Hasn't changed from that one. So that's really cool. Get all lookup table driven coexistence checking. Alright, so that gets us pretty far along. I'd love to run the timer and see why that is. Uh-oh. Yeah, this here still says that this is about half of that, but it could be that the reason it looks that way is because there's a certain amount of time that's not being measured here that is being measured here. right? Like the amount of time it takes to run these timers might be getting counted here, and so that's why it looked so big. I don't know. Yeah, something deceived me about this, but I'm gonna go ahead and take out the coexistence check variable because it's problematic. Now, why is that crashing? Is there something about divide by zero that I lost in the get nonsense? There is. Oh, look at that. If gotcha. So yeah, when I take out that timer for the coexist check, it actually speeds things up a lot. So that explains that whole waste of time. Um, check. Update out grid. Alright, so this is running in debug mode, and it's down to that, which is 2 or 3 times better than what we had at the beginning of the day. But if I put it in this mode, then we can see, compared to this, exactly how good it is. Oh shit. I'd like that to run on debug level 5, please. So let's see. This number here is definitely bigger than that number there, because we're doing all that pre-processing now. And then there are 4 spaces here, and 3 here. So it's an order of magnitude better. It's actually like, I don't know, 1/4 this at the time. It takes about 1/4 of the time it was taking with that lookup table. So that's good. I still think that you could get a lot more speed out of it if you did what I was explaining at the beginning, or not at the beginning, but earlier before I put the table in, where you've put even more zeros in the table. Right now there's more ones in that table than there need to be, because the table only contains information about where 2 guys overlap. But what we could do is we could also go so far as to you learn information about what the neighbors teach you to the farther neighbors. Like a near neighbor could teach you something about a farther neighbor, and so you'd be able to very quickly eliminate a lot of possibilities just by having sort of pre-processed patterns of propagation, so that you don't have to do the full propagation every time. You have like, well, this 5 by 5 pattern is pre-processed for this particular sample, so we can propagate farther faster by sort of doing more pre-processing. I think I'll play with that on my next video, because as I said, I can in my head understand kind of how I do that. I would take what I currently have and then run a propagation system in place during the init stage, but that's getting a little bit too much for today. So there we go. We're about at the end of the day. I'd say 4 times faster than we were at the start of the day after playing with a lot of different things and finally deciding to make the lookup table. We also eliminated a lot of redundant stuff. We got another big improvement we made was to get rid of the coefficients at the beginning of the day. So yeah, I'm going to say there we go. Let me push this late. Well, I'll push it after because I don't remember how. I never remember the name of the repository and all that. And I'll probably end up like typing my credentials on screen if I'm not careful. So anyway, that's it for today. That's it for the year. Thank you for following along all this time, everybody, and I will see you guys in 2017. Bye bye.